No, there are only two participants. No. I was thinking of, yeah, because this reflection. I see. Better. Yeah. This. Yeah. I see. Yeah, much better. I think it's this. Yes. I'll give it to Loga later. He's here.
Okay, maybe we can get started. We are very happy to have Anurag with us today. He's going to talk about his recent work on quantum fields on maximally sliced PTs.
Thank you. So I will talk about this work, which we put out not very long time ago with Naveen and Spenta, both of whom are here in the audience. So let me get started. Okay, it's frozen. That's okay. Thanks. Okay. So we broadly consider two problems in black hole physics. The first is the question of diffeomorphism invariant operators in a black hole background. Actually, this could be more general. You can consider in any background. And the second is how does one describe the time evolution of infalling states as something falls into the horizon. Now, I will try to convince you that both these issues are addressed by correct gauge fixing. After complete gauge fixing, for example, if you consider a scalar field, becomes a diffeomorphism invariant degree of freedom in semi-classical graph. The same gauge choice will give us a foliation whose slices probe the black hole interior and allow us to describe infalling states. While many of the things I say will hold true in higher dimensions, I will mainly, in this talk, focus on the two-sided BTZ black hole setup.
Probably talk about it, but this third point about gauge fixing will make scalar field. You mean still in this boundary sense that you have to take some boundary limit, and because there are these Hamiltonian and bulk constraints.
No, directly in the bulk. I'll work in the bulk.
So it's a local degree of freedom which is different.
It will become a local degree of freedom, yes. Okay, so let me give a summary of our work. So we work in the Hamiltonian formulation of GR. The Hamiltonian and momentum constraints are dealt with by fixing the maximal slicing gauge and the Dirac gauge, respectively. So specializing to 2+1 with two asymptotically ADS boundaries will show that the above gauge is fixed correctly without any residual gauge freedom. We then explicitly construct the smooth maximally sliced foliation of the two-sided BTZ black hole. So the leaves of this foliation that we obtain will, one, cut across the horizons. Two, they will asymptote to the boundary time. Three, they will exclude the past and future singularities. And four, very importantly, the lapse remains non-zero even at the bifurcation surface. We then go on to study the dynamics of a massive scalar field in the maximally sliced BTZ black hole background. In the semi-classical expansion in square root G Newton, working up to quadratic order, we will note that the scalar field and the metric fluctuations do not mix at this order, which is, yeah, that's right. Well, this analysis, this first bullet point is actually general for all dimensions. Yeah. So in 3D, you're right. There are no metric fluctuations. You can just put them to zero. There are yeah. I'm working in Einstein. Okay, then we will write down the scalar field Hamiltonian, which propagates along maximal slices in terms of a discrete set of mode functions that are smooth across the horizons. These modes mix the boundary operators from both the sides, the left and the right, because we're working with two-sided geometry, and are appropriate linear combinations of the Hartle-Hawking modes. This Hamiltonian will be completely gauge invariant operator living in the product of two CFTs associated to the two boundaries, and will describe time evolution of CFT states and or operators, which I'll call the boundary description of infalling. Now our results are valid for evolution times smaller than the scrambling time, during which the fully extended BTZ solution continues to be a dominant saddle point of the quantum gravity path integral. So this is the basic summary. Now I'll just go ahead. So now we'll discuss the gauge fixing in the Hamiltonian formulation in some detail. We are in ADS, yes. Yes, I'll work in ADS. No, so you have this, if you perturb it, for example, by this Shankar-Stanford type. So you go back in time, insert a very small order 1 energy perturbation. Then when you come back at order at t equal to 0, the geometry gets significantly modified after times of order scrambling time. That's the statement I'm trying to make. No, it gets disconnected. The two side gets disconnected. Sorry? It's like a shock geometry. Yes, that's right. Right. But that's what I have in mind. Like the geometry can get modified. And I know like explicitly at scrambling times, the geometry does get modified if you add a perturbation. Well, itself at the scrambling time, I need to include that back reaction.
I think the confusion after including the back reaction at late times, it's still a modified BTC geometry only, right? Just mass has been increased or something.
Right.
You're saying the bifurcate horizon as stretched.
Right. Right. Yeah. That's yeah. Yeah.
Yeah,
I
that's
should be. Yeah. Yeah. That's right. Yeah. Yeah. Right. Yeah. That's the statement. Yeah. 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 Sure.
Part of my confusion is also, like when we talk about dominance and all these things, usually we just take the Euclidean path integral and which only anyway has the exterior.
Yeah.
So full whether it's a fully extended solution and all is sort of
Well,
not-
I am interested in Lorentzian physics.
that's true, but
Yeah.
I'm saying the dominance of the path integral will not tell you about this other shock, really. Euclidean path. Okay. I'm guessing it's the Euclidean path.
Lambda t, basically. The Lyapunov. Yeah. Yeah. Right.
I understand that integral.
Yeah, that's the
boundary correlation.
I agree with that statement, but we allow yeah. So if you restrict yourself to time ordered correlation functions, then I agree our analysis will hold for larger times, but at least it will hold to scrambling times, even if you allow for out of time ordered correlators. Yeah, yeah. Yeah. Right, right. Yeah, I agree with that. That the path integral that will allow you to also calculate out of time ordered correlators. Well, at least two for because I have in mind 4-point function. Yeah. Yeah. But this is just to mention that we are aware that our whatever I'll be talking about can fail in certain circumstances. This is just to say that I'm aware of the fact that our formalism can fail in certain regimes. That's all I'm saying.
Maybe the extent that BTC is dominant.
Right. 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 Yes. 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 That's all I'm saying. Yeah. Okay, I'll go on. So let me just.
Do you want to actually,
Yes. 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 In semi-classical gravity, yes. Yes. Yeah. 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 Okay, so I'll talk about the gauge fixing first. Then I will explicitly put the BTZ black hole in the maximum slicing gauge, which is one of the gauge conditions I mentioned. And then finally, I'll study the scalar field on the maximally sliced BTZ black hole. So let's go ahead. The Hamiltonian of GR is just given by this expression. The N is the lapse and the Ni is the shift. H perp and Hi are the Hamiltonian and momentum constraints. I've also included the boundary term. And there is also a scalar field that has been included as a part of this action. So kappa square is square, basically kappa square is 16 pi g Newton. Yeah. So it's yeah, it's just keeping track of the coupling constant. Right. So the Hamiltonian constraint and the momentum constraints, they generate space-time diffeomorphisms. And from the point of view of phase space, these are first-class constraints that satisfy this surface deformation algebra. So we would like to impose the maximal slicing gauge, which is given by this condition, that the trace of the conjugate momentum pi ij is 0. So now one of the first things you do when you impose a gauge condition in Dirac's method is to find its Poisson bracket with other first-class constraints. The bracket of pi with momentum constraints is just trivially 0, weakly 0. But the bracket with h perp is given by this non-trivial object on the right-hand side. It doesn't work actually. Yeah. It's okay. It's okay. Yeah. Stick. It's not a stick. It's like one of the curtain things, I think. Oh. It's okay. Right. So this operator on the right-hand side, I have also included the scalar field. Provided this potential is negative, this entire operator is negative definite as far as small diffeomorphisms are concerned. So therefore, this operator has no zero modes and is invertible. So this invertibility is important to define Dirac bracket. So this will allow me to define the Dirac bracket and therefore gauge invariant observables under the action of h perp. Yes, exactly. Right, that's the statement. Spatial diffeomorphism preserve the particular. Yeah, you're right. You're right. Also 0, exactly. Yes, you're right. Yeah. Hmm. Right. Right, right. Okay, so let's look at this. This term is negative. This term, so I'm working with negative, lambda negative. I work in asymptotically radius spacetimes. So this is negative. This is the scalar field potential. Provided this is negative, this entire operator. Right, I agree. Eventually, I will treat matter in perturbation theory. So this will appear at the subleading order. So they will. So the scalar field part won't even be there. But the statement is that if you have a matter field, if you have a scalar field, then the potential is negative. If you have any other matter field, as long as it satisfies strong energy conditions, this operator is invertible. That's the statement. Yeah. Yeah, that's right. So whenever the potential is positive, I can only treat that problem perturbatively, in the sense that at this order, none of the matter fields will be there. In kappa, semi-classical expansion. Sorry? I have unfortunately put kappa equal to 1 here. The point is everything else has a 1 upon kappa square, right? Yeah. Is that all right? Sure. Right. So then.
What is the statement that the Hamiltonian?
Right. Right. No, I don't think. So let's say instead of this h perp, you had the full Hamiltonian. So what will right? So the full Hamiltonian has a lapse times h perp. So then this operator will act on the lapse. right? So the equation for lapse will be that this acting on the lapse is equal to 0. But in asymptotically radius spacetimes, you would like the lapse to grow. So it's a non-normalizable mode, 0 mode. So that's the statement I make here. There are large diffeomorphisms which do not vanish at the boundary that are 0 modes. The lapse, in fact, is the thing that satisfies this equation. So there'll be 0 modes, but it's not like anything is rolling down. So when you impose the pi equal to 0 gauge, you would like it to be time independent, preserved in time. Pi dot should be 0, so that pi always remains 0. Yeah. So I don't think that rolling down intuition is correct. This is trace of pi. Yeah. That's what I want. Yeah. Yeah. Okay, so since this operator is invertible, what I have really shown is that the pi equal to 0 gauge, the maximal sizing gauge, can be fixed locally in the phase space. But you can ask, can we fix it globally in the phase space? And the answer to that question is yes, you can. To see that, you start with an arbitrary point G prime, pi prime in the phase space. So it's useful to look at the figure. So this vertical column is the pi equal to 0 subspace. This horizontal thing is the h perp equal to 0 surface. You satisfy the Hamiltonian constraint if you are sitting on that. So you start with an arbitrary point in the phase space, G prime, pi prime, such that the trace of pi prime ij is 0. You start with that. Now you can do a Weil transform, which uniquely takes you to an intermediate point, which I call G twiddle, pi twiddle, satisfying the Ricci curvature equal to constant 2 lambda. This is just an intermediate step. Then one can do a further Weil transform. Spatial, yeah, because all this is spatial. We are working in the phase space. Yeah. One can do a further Weil transform to G and pi, and you want this to satisfy, you want that to be on the h perp equal to 0. You want it to satisfy the Hamiltonian constraint. When you plug that in the h perp, the Hamiltonian constraint, what you find is this equation. This is known as the Lichnerowitz equation. Lambda is the Weil parameter. Now, this equation has been rather well studied, especially in ADS. So there are theorems by math relativity people, which basically say that the solution exists and is unique. So the existence and uniqueness of solution of the Lichnerowitz equation in asymptotically ADS spacetimes guarantees that any arbitrary point you started with can be brought to the h perp equal to 0, pi equal to 0 subspace, which means you can always fix the Hamiltonian constraint uniquely once and for all. So once you have done that, the independent degrees of freedom are the Weil classes of metric. Right. Yes. This theorem is very importantly hinges on the fact that lambda is negative. Yeah. There is also a boundary condition on lambda that it vanishes on the boundary. So the independent degrees of freedom are Weil classes of metric, so metric up to a Weil factor, and traceless momenta because you put pi equal to 0. Now, for the momentum constraints, we fix the Dirac gauge, which is given by this equation. The Dirac gauge is Weil invariant, so you can put that condition on any other metric which is Weil related to the original metric. So again, you can find the Poisson bracket of this thing with the momentum constraint, and it's given by some complicated operator. And first, it was shown by Dirac that this operator is invertible in small distance expansion. Now we are eventually interested in 2+1 dimensions in BTC black hole. It's a known fact that one cannot fix Dirac gauge or any other gauge for the momentum constraints globally in the phase space, unlike the maximal sizing gauge. So we anyway have to specialize to the neighborhood of the classical geometry we are interested in. So that's what I'm going to do. So the way I'm going to fix the Dirac gauge is following. A constant curvature metric with r twiddle equal to 2 lambda on the r times s1 with the topology r times s1, which is basically the topology of spatial slice of an eternal black hole in 2+1, can we always put into this form. This you can show by using some results from hyperbolic geometry. I will discuss it if I have time. And one can check that this metric is always already in the Dirac gauge. So here I've specialized to 2+1 dimensions and the BTC black hole. Right. So this phi goes from, phi goes from 0 to 2 pi. Theta goes from -pi/2 to 2+pi/2. And I forgot to mention that there is this parameter m, which you can think as the modulus of this geometry, which will play an important role. It will be one of the coordinates of the phase space, reduced phase space. Once you have fixed these gauges, you can solve the momentum constraints. So in the Dirac gauge, the momentum constraint after some manipulation just become two decoupled Laplace type equations, which you can solve with these boundary conditions, which are appropriate for the BTC black hole. So you get this solution. So C here is the other important parameter. It's just the boundary value of the phi component of the extrinsic curvature. Once you have this, you can plug this into the Lichtenowitz equation to again find what lambda is. So then you have determined everything in terms of only two pair of real numbers. One is m, which was the modulus, and another is c, which went into as a boundary condition for k phi. So this is the reduced phase space of pure gravity with the topology of the cylinder. And when you treat the scalar field perturbatively on top of it, you will also get the scalar field. That's the reduced phase space. So I want to say something about perturbation theory. This is the perturbation theory in kappa, semi-classical expansion. So you start with the action, the gravity action. You plug in, you expand all the fields, lap shift, everything in kappa, and then you look at the action, which is also expanded in kappa. So S hat is the background on chill action. The linear term will vanish because you're expanding around the solution of an Einstein equation. And from the quadratic term, you can read of the Hamiltonian at this order. So the Hamiltonian has this form. So the alpha and beta are the subleading lapse and shift, and what they multiply are the Hamiltonian and momentum constraints at this order. And you can see that they only involve the metric and its conjugate, the metric fluctuation and its conjugate. This analysis is in general. So if you're working at quadratic order, you see the scalar field does not at all talk to the metric fluctuations. Similarly, you can expand the gauge conditions, the pi equal to 0 and the Dirac gauge condition. That also does not involve the scalar field. So what this means is that after you fix the gauge at leading order, the scalar field is a gauge invariant and local degree of freedom with this Hamiltonian. Everything that enters here is the background, lapse, shift metric, and so on. So that is what I meant. It's if invariant local degree of freedom. Okay, so now I'll go to the next. Sure.
This is not in conflict with whatever like work of Subrat and all.
No.
There are no.
Those are non-perturbative statements. I mean, non-perturbative in the sense, if you look at the full Hamiltonian or momentum constraint, of course that involves the matter fields. But when you do an expansion, you see that and you restrict to yourself to this order, you clearly see that they do not talk to each other.
That just means that the whatever commutator you're measuring is of higher order. Like it's at kappa square order, whereas you have truncated at kappa. But to satisfy constraints, you really want things to be zero.
No, I mean, if I'm consistently working in semi-classical expansion, I should do everything in semi-classical expansion. Why should I impose something at higher order, but for other things, I only work on less order? So consistently, I will always work. Let's say I work on this order, I should impose everything at this order, not at higher orders. Anyway, that does not affect the... yeah, one can systematically do the higher orders, right? Exactly. No, they don't. Yeah, you can solve for them in the gauge I mentioned. Yeah, you can solve for them. Yes, that's right. It's something that so it goes to the standard ADS. It grows linearly with R as R goes to infinity. Yeah. Yes. And in the interior, it has a minima somewhere in the center, but it never goes to zero. Right. So the term is like n squared dt squared. So the lapse itself goes as R by n. Yeah. So it grows linearly because that's the boundary condition you would like to impose. In the middle, it turns out when you impose pi equal to 0 gauge, it never becomes 0. It's, I mean, of course, I can draw a rough. So these are the two boundaries. Right. So it doesn't go to 0. Let's say this is the 0. This is the... We have the exact solution. I'll show you, in fact. Okay, so let me go on. How much time do I have? Okay. Okay, sure. Thanks. Right. I also prepared for 1 hour, but let's see. Okay, so now I'm going to put the BTC black hole in the maximum slicing gauge. So what I do is that I start with a metric of the following ansatz. Here, phi coordinate is the same as the angle coordinate you were asking about, but I've traded theta for a more familiar r, areal radial coordinate. And this alpha, beta, and a are unknown functions, which I have to find by solving the Einstein's equation together with the maximal sizing condition in 2 + 1 with 2 asymptotic boundaries. So the time here I've called t bar. It's different from the BTC time. That's why I even call it t. But sorry, your question was something else. I haven't reached there. So you solve this equation. It's just, you can simply do the integral. You get a constant in R, but it can be a function of t bar. So that unknown function I've called capital T of t bar. It's something to be determined. It's not determined yet. I'm just highlighting how I solve the Einstein equation. Yeah. No, it doesn't. That's why I have to solve for it. It's a general, yeah. These functions are unknown. I have to find them. Spherically symmetric, yeah, that's right. So the first step was to solve this equation, which is one of the momentum constraints. That gives me this. Then I solve the Hamiltonian constraint, which is again a first order equation. It only involves derivative, radial derivative of A, which I can again easily integrate to get this. So I get one more constant, which which will be the mass of the BTC black hole. And one has to show that it's time independent. You can use another equation to show that it's time independent. One point I want to highlight in this slide is that this function, which is the GRR coefficient of the metric, has singularities at at the positive roots of this equation, and therefore this coordinate chart actually fails somewhere in the interior. No, that's not the horizon. It's some locus, and it fails exactly at r equal to r plus with the bigger of the roots. And so what I want to say is that I'll need two charts, one connected to the right boundary, one connected to the left boundary, and I have to somehow glue them together at the point where they fail.
That's some coordinate.
It's a coordinate singularity. Yeah. So one can also solve all the other equations and get a solution. So this is the solution of my Einstein's equation. I've determined alpha, beta, and a up to this function t of t bar. So let me go ahead. But how is the solution that I showed you in the previous slide related to the BTZ black hole? So I can find that explicitly by doing a diffeomorphism. Since it's the boundary value of k phi at the asymptotic. That's all. It's yeah. So if let me maybe make a connection to something I said earlier. So when I was here, now the k with lower indices actually do not transform under a while. So you can remove the twiddle. These are actually the physical space-time extrinsic curvature. As you can see, this is the boundary condition. C is the boundary condition. So it can be a function of time. That's precisely the function which I find when I'm explicitly trying to solve this Einstein's equation. Okay, let me say one more thing. Yeah. Yeah. Well, not boundary. It's the bulk also. Yeah. So this function will turn out to be a monotonic function of t bar. And so you can think of this as time itself. You can trade capital T for t bar. And so this this component of the extrinsic curvature in a way functions as a time coordinate. That's one interpretation of this. But yeah. Yeah. Right. So let me show you the equation which actually determines it. Finally, after a lot of manipulation and matching and everything, the final equation on this slide determines capital T of t bar implicitly in terms of the boundary time t bar. Not the boundary time, just the time t bar. But if you want to know how it looks like, so I can draw it. So as a function of t bar, this looks like it starts from 0 and then approaches a maximum. This is how the function capital T of t bar looks. No, it is the time, but because this function is monotonic, you can think of capital T itself as a time. Sorry, my bad handwriting. Yeah, sorry, my handwriting is terrible. T bar is the time everywhere in the bulk. In particular, at the boundaries matches the boundary time. That's something I would impose. No, it's different from that. It's the same as BTZ time only at the asymptotic boundaries. Right.
a simulation for
Right. Yeah, that's right. Right. It's like this. Yeah. So I think I'll just skip all these details. The main thing that was undetermined was this function capital T of T bar, which I get by doing a diffu to BTZ and then matching the left and right charts. So that determines everything. So now my entire solution is alpha, beta, A, all those functions are unknown in terms of this function capital T of T bar. But there's one more thing I would like to do is that I don't like the fact that these charts fail somewhere in the interior. So the way I will fix it is by introducing a new coordinate x, which I call the wormhole coordinate, defined as follows. So x is 0 exactly at r equal to r plus, the point where the two charts meet and fail. So it will turn out that for negative x, I'll cover the left chart. For positive x, I cover the right chart. So with a single coordinate, I'm able to cover the entire wormholes from the left boundary to the right asymptotic boundary. So this is the metric, but let me just discuss some of the properties of this metric.
The fact that there's a horizon in BTC, how is that visible in whatever coordinates?
So
because there also things fail, right? Coordinates technical, I mean, some sense fail, regenerate. Something.
Yeah, but here it's all well defined. But in terms of this new coordinate x, it's the horizon is at plus minus r minus, or r minus was the other root.
Okay.
Yeah. So this is the definition r plus minus. X equal to r minus is the location of the horizon in these coordinates.
And this small r coordinate is what we'll also call r in.
Yeah, the BTZ r you are familiar with, or the Schwarzschild r you are familiar with. It's exactly that.
R minus square plus r plus square root.
In BTZ. Yeah.
Okay.
Yeah, let me show the figure, it'll become clearer. So the maximal slices extend from the left to the right asymptotic boundary while smoothly cutting across the horizon. So let me show the figure. So the left you see this Penrose diagram of the BTZ black hole. On the right-hand side, I have the Kruskal-Zacharias diagram. So these blue curves are constant T-bar lines, which are also maximal surfaces. Because of that, I have solved that I have imposed that the constant time surfaces are actually maximal. They're the same, but the value of, so you have to figure out if you're at this T-bar, then you can read off what is the capital value of capital T. So, right. It look the same, yeah, exactly, yeah. Right. So the slices, as you can see, for example, this slice goes from the left boundary all the way to the right boundary, smoothly cutting across the horizons, and everything is fine in the interior, the entire coordinate. So r equal to r plus in this thing will exactly be at the center of this line. So the right chart and the left chart I mentioned would have failed exactly at the center, but then I've smoothly joined them by introducing this new coordinate. So the x coordinate goes from minus infinity on the left boundary to plus infinity on the right. Yes. Right. That's right, because that's the next point I was going to mention. That in these coordinates, what happens is that as T bar goes to infinity, these slices approach this orange slice. There's a maximal slice as T bar goes to infinity. It's some constant R surface, which beyond which these slices cannot probe.
basically an infalling observer.
Exactly. So that happens at this point. But one thing I would like to emphasize is that this is something that is useful in, for example, in numerical relativity, where they actually want to avoid the singularities because they don't want the code to, throw up infinities and so on. Yeah. Right, exactly. They fail on this.
At some point of time.
Right.
At some finite proper time.
Yes.
The observer would kind of stop.
Precisely by this.
Like what happens to Schwarzschild time for the equal observer.
Yeah. Now it's pushed somewhat further. Yeah.
According to the infalling observer.
Yeah.
Faster, no? Has to reach infinity.
So you have to cover a very small distance in an infinite amount of T bar.
Oh yeah, I was computing inverse. Yeah, proper time is finite. Yeah. And dt bar is infinite. Yeah.
Infinite.
Is there some special geometric meaning to this final slice?
Yes. It's a constant R surface given by this particular value. No. This little r, in the BTZ r, the areal radial coordinate. Yeah, it has a specific. Exactly. Yeah. On the boundary, it goes all the way to infinity.
It covers all of it.
Right. Yeah. Yeah. It covers this interior, right? Yeah. Right. Yeah. So there is. Yeah. But before that, I want to say a few more things. The lapse remains finite at the bifurcate point. That's why the slices take off. Otherwise, they would be just stuck at the bifurcate horizon. And I have an explicit. I can write down the explicit coordinate transformation. And most importantly, the time t bar at the boundary is the same as boundary time. So it's same as t on the right boundary, same as minus t on the left boundary, because time on the left runs backwards. Sure.
Talking only about BTZ, but most of what you're saying is slightly general, right?
Yeah.
In IID spherical black hole, we know that the singularity also bends down. So is this gauge fixing and all compatible with that?
I think so, yeah.
Final slices still reach before?
I think so. So these slices, they're called maximal slices for a reason, is that they maximize the volume. Because most singularities are volume crunching type, these slices are sort of repelled from the singularities. So they will always avoid the singularities.
That's good.
Yeah. So you can also consider these asymmetric slices. So basically on the boundary, the T bar is same as the boundary time, but there can be a constant shift. Basically the choice in choosing the origin. If you choose a different origin, you get a different sort of slice. So I've just shown that. This is a 3D embedding of the cylinders, the wormholes. And as time increases from left to right, the wormholes stretch along the length and shrink along the circular direction. Another observation. So now to come back to your previous question, there is a second family of maximal slices, which lives completely inside in the interior. In fact, you can also label them by T bar, and they start somewhere close to the here. And as T bar increases, they approach the same limiting slice, but from the other side. So together, the two families will cover the entire black hole geometry. So it's true, you need two charts, but there is another chart that covers the interior. They are spatial, but they are not Cauchy. They are actually spatial. Yeah, they are. Yeah. No, they are spatial. Yeah. Okay. So that's the thing. So finally, I come to the study of scalar field in the maximally sliced BTC black hole background. So recall that at quadratic order in semi-classical expansion, the scalar field is gauge invariant and physical degree of freedom after gauge fixing. Now we would like to quantize the scalar field with T bar as the time. So along these maximal slices. Sure. Right. Yeah, that's right. Yeah. Yeah. Yes. So at that place of the orange curve, you have to change coordinates. That's right. All right. So we would like to solve the Klein-Gordon equation in wormhole coordinates, but that turns out to be rather complicated. And
This is not
it's not static. Yeah, that's the important point. The only killing vector I think is the del phi, which is translating along the circle. That's all. Well, no. So right. So let's say let me go back to this figure. Right. So in this region, let's say, and similarly, the reflected thing here. So between the two orange curves, the top and the bottom, I don't think there is any other killing vector. Okay, yeah. Right. So it has also. Yeah, you're right. Yeah. Okay, yeah. Yeah, basically the boost. Yeah.
those states should be the same.
Right.
Those should be the conserved quantity.
I see. That's
But there are conserved quantities.
That's a. I see. That's a good point. I haven't actually worked. We haven't tried to work out the action. Yeah.
We cannot.
Can actually take the BTC, giving vector and just
Yes. But I'm not sure if that will help me in solving the Klein-Gordon equation. I'm not sure. Well, yeah, because in the interior, right. Yeah. Exactly. Yeah, that's the point.
But the point is that there is something which integrate over a
I see. Yeah.
Mhm.
Right, right. The stress. Yeah, that will be. That will. Yeah. Yes, 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 yes. Right, right. Yeah. I agree with you. Yeah.
That will be a property.
Great. Yeah, yeah.
He's written that you just solve in some coordinates and then transform the final field.
Yeah, that's what we are going to do. Yeah. Yeah. So the point is that there's no time-like Killing vector in the entire geometry, or at least the part that is covered by these maximal coordinates. So, however, I must say that if you give me a initial Cauchy data on some Cauchy slice, then there is no problem in solving this equation numerically, since all my coordinates, metric, and everything is smooth and well defined. However, we still want to solve go as far as possible analytically. So for that, what we do is like we solve the scalar field equation separately in the wedges, like the exterior and in the interior and so on, and then pull it back on these maximal slices. That will basically give us the solution in these coordinates. Yeah. But the quantization is also straightforward. I mean, the quantization is also straightforward. Yeah, yeah. Yeah, I agree with that. But yes, it's a non. Yeah.
There's a coordinate change, of course.
Yes, yes.
But, there's also a Boblibo transfer.
Yeah, yeah. We will do all of that. Yeah.
You're saying you know the Boblibo transfer from this usual coordinate.
Not directly, but let me come to that. Let me go through it. That's what all comes next. Yeah.
But the vacuum is not the same.
Vacuum is not the same. Exactly. It's different. Yeah.
So you have to like shift the vacuum.
Yes, yes,
And it
yes.
doesn't transform in a way like.
Yeah, yeah.
It's not even clear there's a vacuum.
Yeah, we'll come to that. Yeah, yeah. Okay, let me go ahead. So you can solve the scalar field, for example, separately, let's say in exterior region 1. So my convention is region 1 is the right wedge, region 2 is the left wedge, and future and past. That's my convention. So it's easy to solve for the scalar field, let's say in just the exterior region, one of the 4 wedges, because there is a time-like Killing vector. So you can separate variables. For example, you can write this f as something e to the minus I omega t times e to the minus iq phi times a function of r, and that will satisfy some hypergeometric equation. So you can solve that, and you can get this mode expansion. So these f omega q are normalizable mode function with respect to the Klein-Gordon norm and are given in terms of the hypergeometric functions. All this is standard stuff. Now, the dual boundary operator to the scalar field can be obtained by the extrapolate dictionary. So basically, you multiply it by r to the delta plus, take r going to infinity, and that's the dual operator, which I've written here. Now, there's a similar expansion in the left region, in the region 2, and I differentiate the quantities in the left wedge from the right wedge by adding this twiddles everywhere. So this is standard. So to get the solution in the interior, one can follow this prescription of Unruh, which basically says that. So it's easiest to see this in crustal coordinates. So the crustal null coordinates, capital U and capital V. The location of the horizon is at U equal to V equal to 0. The mode functions actually have a logarithmic branch point at the location of the horizon. So Unruh's prescription is that you cross the horizon in such a way so that the mode functions remain are analytic in the lower half complex U and V planes. So that's the prescription that gives you solution in the interior also from the exterior solutions. So with that, you know the solution in all the 4 wedges in the exterior regions as well as the interior regions. And these oscillators, which multiply these mode functions, are related to the oscillators on the previous page, these A and A twiddles by standard Bogoliubov transform. So at this point, this is all known stuff. Yeah, standard slicing. But this solution is still not a solution everywhere because it fails on the horizons. And the easiest way to see is that the derivatives of these mode functions diverge at the horizon. So that is one problem that is not appreciated, and we are going to fix that now. It's not smooth. So let me say normalizable. No, so there are 2 boundaries. So normalizable both on the left and right. So let me that's exactly the point I'm trying to make here. So let's look at these Hartle-Hawking mode functions. So suppose you're in region 1 and then you zoom in close to the horizon. So the mode function looks like this. So for example, let's look at this term. It looks like U to the I omega. So when you take a U derivative, it brings down a 1 upon U. And as you go close to the horizon, as U goes to 0, it diverges. So the mode functions are not smooth. And this is true for all higher derivatives. The mode functions are not smooth exactly on the horizon. Away from the horizon, they are fine. On both sides. Now we will cure this problem by working with yet another set of mode functions. And the way we get that is that we smear this Hartle-Hawking mode functions, this H omega, with Hermite functions. So you take the Hartle-Hawking mode functions, you multiply them with this Hermite functions, which are the eigenstates of the harmonic oscillator, and you integrate over all omega to define this new mode functions, which I call G, this typewriter G. It's exactly on the horizon. Right. Right. That's the prescription I was telling. That's how Ru tells you how to make that choice. Yeah, exactly. Yeah. Well, so if I recall the first, in Unruh's paper, he also does the Rendler, the flat space Rendler example. So there, this condition translates to positive energy, positive frequency solutions in the light cone coordinates. So that will still be true, that on the horizon, these are positive energy, positive frequency solutions. That's basically the prescription. Right. So I've defined these new mode functions G, and they, again, when I come close to the horizon, they take this form now. And now you can see that, let's say I take the U derivative again. So that brings down this e to the curly theta. I don't know if you can see it. This e to the curly theta. But this Hermite has exponential e to the minus theta square by 2. So this integral will always be finite. Hermite function. So Hermite polynomial times the exponential, appropriately normalized. Yeah. Right. In fact, all derivatives will be finite because the Gaussian will overwhelm any thing that the derivatives pulls out. So what I've achieved is a new smooth global expansion of the scalar field in terms of these discrete set of mode functions. Right? So now this is a solution everywhere on the full black hole geometry, including the horizons. That was what was missing in the previous with this solution.
Horizon, but if you just sum over infinite modes, you can remove.
I think
there are probably many smearings you can just do.
Yeah, I'm not saying that this is a unique smearing. There could be others, but this is definitely what works for
so
us.
You're solving and just integrating in omega. And
yeah, this one.
Doesn't depend.
Right. I had a slight doubt.
Sure.
In what Loga was saying earlier, you just take the Klein-Gordon in this t-bar coordinate, the thing that is regular across the full thing.
Exactly, yeah.
If you solve the wave equation in that, won't it automatically ensure whatever solution you have written down is already regular?
Exactly, but if only I could solve it analytically. I cannot. It's very complicated, right? I showed you the equation. Where this lapse and shift are, those very complicated
given the
expressions.
Fact that it has the same number of isometries that the thing you're solving has.
Right.
The radial equation may look messy as hell.
Right.
But
yeah. That's the sort of thing that's always in the back of my mind. Yeah, I have solved it, but not directly, but going through this sort of.
Because you know. Because you know diffeomorphism from U.
Right, that's the point I make here, is that once you know, once you know the expansion in terms of these coordinates, which are still in some sense in terms of the critical coordinates, you can do a diffeomorphism to x and t bar because there's a smooth diffeomorphism between the two, and therefore you have a solution in x t bar coordinates. So because I could not directly solve the Klein-Gordon equation in x t bar coordinates, I went through this, alternate route, but I have the solution. That's the claim. I have eventually solved the Klein-Gordon equation in x and t bar coordinates. I fixed that problem, right? So these modes had the problem, but then I redefined these new set of mode functions, which don't have any. It is complete, yeah. The Hermite completeness. Yeah. Yeah, it's an UV dependence is the same. Yeah. So this will not. Yes, they are. Sorry, what? Sorry, eta is just the surface gravity. Yeah, I define it somewhere here. Yeah. 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 No, no, no. It's an exact solution.
Was the Fourier mode.
But these are
H of
right.
You're saying the Hermite polynomial itself is
Omega is the parameter
no, with the e to the I omega t factor.
Omega has all
It has all of that.
Omega has
Yeah.
Q is
e
like
to the okay, it has.
You say everything has been pushed into
And you're
this.
saying some arbitrary function of omega times this sum over whatever omega is also a solution.
Yeah, yeah.
Okay.
It's in some sense a basis change,
Mhm.
right?
Mhm.
That's all it is.
So like from Fourier basis, you just want to go to this Hermite
Yeah,
basis.
yeah, Hermite basis.
mentioned that right
Was right.
Fourier moves like you're saying the Hamiltonian the oscillator wave functions are these. This is for these functions.
Mm-hmm. Yeah. Yeah. Yeah.
Those functions are not kind of it's a bit like you're taking the Fourier basis and like easier.
Yeah.
A stronger than we would usually.
we assume that
Yeah.
No, no, no. Put a wave packet, but that's the kind of localizing.
infrared cutoff. No, but
You don't put a then also put a UV cutoff. But then like you try to then here you kind of counter. What I'm trying to say is that we are looking at modes which have some stronger condition than usual
see if you want to recover this number of GMUs.
Right.
No, but all of them will die off at last.
No, no, no. Yeah. Yeah.
The number of basis components you have some limit you have to have large coefficients for large
we can argue. The point is that the space on which Fourier analysis works is of infinite.
Right. Right.
Space on which the completed wave functions are kind of
L2 now. Yeah. Yeah.
It's a kind of more from
Yeah.
I don't know how to solve it, but it's a bit of one of these
Yeah, maybe. Right. Right.
Maybe another way to say it is that after you transform everything, let's say I go to this maximal slice
Yes.
and I take the operator and I calculate the 2.5.
Okay.
And then I look at the high energy behavior of that. This is OP. Does it look like standard OP here?
Okay.
That's the question of whether you have really done violence to the high energy. You want to kind of quantize things.
Yeah.
Such that
the UV. Yeah.
in curved space time, especially when you don't have any obvious sign like I said.
Yeah.
All that you have is an operator algebra.
Yes.
Okay. And you just want to the main condition, you want to put the scalar operators near, geodesically near each other.
Yes.
Okay.
Yes.
Okay. Then the OP should kind of reproduce the OP structure
in flat space. I agree with that. Yeah.
So that is a
Yes.
That is the only thing you can impose. So impose the, otherwise, the quantization is pretty, wild, except that, like the main condition is that when operators come together.
Yeah. Okay. I agree with that. So.
Should be reproduced. Now the question is if you smear it and do all this. Okay. The question is that they sum to the.
So I have not explicitly checked this, but my guess is that it will work out. It will have the UV. Right.
There was a vacuum.
Yeah, but the vacuum will not preserve any.
Not slicing on this basis.
Here it's okay.
Yeah,
the point is that, like.
It's still alive like that.
Yeah, that's true. These oscillators also annihilate the Hartle-Hawking state. Yeah, exactly.
Point is that, see, for example, you can do one thing. You can take a invariant theory. You can put a UV cutoff, some smooth UV cutoff. Then if you try to calculate the P of phi of x, phi of y, you will see that, let's say you kind of be completed in the string theory. What will happen is that when you try to bring them, it will look like one of these, but at very close distances, it will fall off faster. Usually,
yeah.
No, even masses don't matter. For UV behavior, masses don't matter. Okay. The statement is that UV behavior of Green-Gordon theory is just kind of bring them very close. You can confirm a power loss, right? Because just treat Green-Gordon.
Yeah.
Right? It's like very high energy. You just get, OP. The question is that, but you could imagine that you have kind of, killed the UV modes in such a way that, let's say they start falling exponentially. Okay. When you try to bring them to be softer. There's no like power law follow, but like some string theory like one. You can have an exponential form. Okay. It is a statement that in string theory that these are extended of. So they kind of cross sections go down. Okay. So the question is that like whether that something like that has been done, whether you have put a. But anyway, anyway, the real question is of course what happens.
This is actually shifting here. That is what is happening. Just killing that.
Yeah.
Yeah, but
so if you compute stress tensor in the see that it's proportional. There is a texture energy which is associated. It is killing that. getting rid of the short distance expansion. Rid of the short distance expansion. 2 points coming near to each other.
Yeah, that's
Okay, but anyway, this is a
right. So, so once I have this smooth expansion in terms of these discrete mode functions, and I know that the coordinate transformation from the crustal to the wormhole coordinates is smooth. It's a diffeomorphism. I have so this expansion actually solves the Klein-Gordon equation in the maximal coordinates, the wormhole coordinates. Yeah, I see. Yeah.
Hadamard in the correlation.
Hadamard is first of all this oblique structure usually independent of the.
Yeah.
So there's in unique. Never unique state. What it does is that it fixes a Hilbert space. In the sense that it fixes a space of state, or quantization. This is a theory. It doesn't give you a state. But
other conditions, like the vacuum is next.
the problem is that these maximum strengths doesn't have a lot of space.
Exactly. Yeah.
This is like third space-time quantum. Third space-time has almost twice.
Yeah. Yeah.
So it's not even, so usually everything goes off. There's no vacuum, there's no
Exactly.
there's no particle, there are nothing, right? Except there are some operator algebras.
Right,
so
right.
Okay. And correlation.
So if right, because the Hartle-Hawking not necessarily.
Change the size, you have to change the value.
Yeah.
At this stage, we have not yet. This week.
Also, just to actually calculate the Bogoliubov transformation, I would need the expansion in the wormhole coordinates, right? Then there is a nice way of taking inner products and finding the Bogoliubov transformation. Unless I exactly.
There's no positive and negative. You don't have a frequency.
Right, I don't have a yeah.
You don't have a time-like isometry. Manifest time-like isometry.
But I still
modes don't have are not labeled with.
They're not labeled by frequencies.
So there's no question of positive and negative.
Agreed, but there should be an expansion in some index, right, which will label all my mode functions.
Yeah.
Not frequency, something else.
Yes, but then there's no creation annihilation. Once you don't have frequencies, you don't have positive and negative frequencies. You don't have creation annihilation. Positive, negative, negative. You just
Right.
What you can do that you don't talk about oscillatory dagger. What you do is in general quantum you end up somewhere like this where you don't have frequencies and anything. Okay. Just basically give up everything except correlation. Those exist. You have some phi of x, phi of y, whatever. Some state. Okay. Correlation function in some state. Okay. And if you can define correlation function in some state, that defines this.
Right.
There is a way to
Yeah.
They have like some agnostic.
Yeah.
Whereas one is the complex conjugate of that. Phi star line will norm is 0. Phi I, phi j is delta. J star is minus. The only
It's,
thing that I've seen them exist is simple time dependent situations as well, where you can like the interior of the
yeah. Okay, let me go ahead. What I'm interested in is time evolution of states and operators. So since I know the scalar field everywhere, I'm really interested in the Hamiltonian, the Hamiltonian of the maximal slicing gauge. So this is the form of the Hamiltonian with the slab shift, the metric, everything from the wormhole coordinates. So I use this expansion that I had on the previous slide in terms of x bar and x and t bar coordinates to get this expression. So this Hamiltonian is still quadratic, but it's highly, it's not diagonal, it mixes everything. And these kernels are time dependent, but they are finite. So they have an explicit expression where I know everything because I know all the metric components, I know the mode functions and their derivatives. So this all is finite and well defined. So finally, what I want to do is I wanted to tell you was how do you evolve states or operators depending on what picture you're working in. So this Hamiltonian is Hermitian, completely gauge invariant operator that lives in the product of two CFTs and describes time evolution of CFT states and operators by this evolution operator. So because it's time dependent, you need to have a time ordered exponential. So with this, depending on whether you're working in Schrodinger or Heisenberg picture, you will evolve your states or operators starting from an initial state, which I assume you know. For example, in the slices I showed you that pass through the bifurcated horizon, the symmetric slices, you can always put the Hartle-Hawking state at that initial slice. So this tells you how states. No, I mean, it's just a state, right? I can put it at t bar equal to 0 and evolve it. Sure. Same slice. So let me show you. Yeah, I'm saying here, I can start with the Hartle-Hawking state or some small fluctuations of it, and then evolve with my. Sure. Right. Exactly. That's what I have in mind. Yes. Yeah. That the Hartle-Hawking state. Yeah, that's what I mean. Yeah. So all I'm doing is telling you once I know the state on initial slice, because I know my Hamiltonian and therefore the time evolution operator, I know how they evolve. And with that, I can, they're horrible looking in, but I can still calculate all my correlation functions by closed contour, Schwinger-Keldysh-like contour, because this is all time dependent. Right. So, right. Yeah, exactly. So this E was related to the Cs, the C oscillators, which itself was a combination of the left and right oscillator. So the point, so the point is that this operator, this Hamiltonian and the time evolution operator, is actually a CFT operator which lives in copies of two CFTs now. So you can use this to calculate 2-point functions and so on. That's boundary 2-point functions. Yeah. So that's my final slide. Exactly. Well, if you work directly in the boundary, you don't know that actually. Because on the boundary, yeah. So the first set itself has everything from the boundary point of view. Yeah.
It's a very serious attempt. Serious attempt.
Yeah.
This is like a principle thing. But how to take a hard problem and get rid of evident isometry. That makes life even more difficult.
I'm done actually. This is my last slide. Yeah. Yeah. No. I have some backup slides in case there were questions, but since no one asked me about that, I will not. It's I was hoping that it was meant for Suvrad actually because he so he always talks about I don't know so he asks he would ask this question that what happens when you let's say just do a time translation on the right boundary but not on the left boundary. So what this slide shows you is that let's say these blue ones are the original symmetric slicing. The green ones are the images of my old slices after doing only a right time translation. And they are unique because I fixed the maximal gauge. So one of the points is that when you do this translation, not only does the slice change in, let's say, the right region, but also in the interior as well as the left region, because the slice has to adjust everywhere to maintain maximality. And not only that, I can write the Hamiltonian, which takes, let's say, a slice on this a state on this slice to a state on this green slice.
You mean
a unitary operator? Yeah. So it looks exactly like the one I had for time evolution on both sides, but I can write one which only moves let's say the right boundary, keeping the left boundary. So I just had that slide in case he asked that question. It's a full bulk integrated object. Right. Yeah. It's similar to the Hamiltonian I showed you. It's yeah. That's all.
But then you
Mhm. Yeah, yeah, yeah.
This expression simplifies.
It will simplify. In fact, it'll become time independent because I'll get HL minus HR or something along those lines. Yes, that's right. So, sorry, what? No, no, no. So, see, the point is that the question is, I thought the question was the following. No, no, you can go, right? So I think it's easiest to draw in the classical diagram because the slices, the killing slices just go like this. Those slices never? Right. Hmm. Yeah. So I can describe this evolution also, the killing time evolution also.
All these are maximum.
Yeah, these are maximal slices in a very trivial way because the conjugate momentum itself is zero. So it's not just the trace, everything is zero. That's why they're because it's static, therefore it's also maximum. Yeah. Right. So I had this figure, right? I'll show you. Right. So I had this figure. This is what happens. Oh, sorry. So you start with this, then you move this up, that down, you get these slices. Oh yeah, that's right. Yeah. Yeah, yeah. Yeah, it is in general that complicated time-dependent evolution of maybe if the state is on this slice, it may remain unchanged because I know that under the action of isometry, which is in the boundary theory action of something like HR minus HL, preserves the Hartle-Hawking state. So maybe only for this slice, then state which lives on the slice that passes through the bifurcated horizon, maybe the state remains the same. But for other slices, definitely the state will change. Yeah, type.